Hello all. I welcome you all to this lab course Communication Engineering 2. This video corresponds to the experiment number 2, that is the design and simulation of antennas. So in this video, we will see the design. Let me take the pointer. Okay. So we'll see the design, simulation, and the simulated result analysis of two different antennas. The first one is nothing but the half-wave dipole antenna, and the second one is the array. Okay. With the half-wave dipole antenna, we try to build an array. So I hope you have already done this course antennas and wave propagation in your previous semester. So you might be having an idea of what I'm speaking, right? So you know what is an antenna and what is a half-wave dipole antenna and what is an array antenna, what is the purpose of going into an array antenna. So all these things you might be knowing. So with that in mind, we directly move into the design part. Okay. So coming to the design part of an antenna, that is before designing an antenna, we should be clear with two different things. The first thing is for which application we are trying to design the antenna. Okay, so whether my antenna is going to work for an AM communication system, or my antenna is going to work for an FM communication system, or my antenna is going to work for Bluetooth or Zigbee or Wi-Fi. Okay, so this first I need to define. I need to decide. Okay, so for which application I'm trying to design an antenna. Okay, so if I'm trying to design an antenna for AM communication system, we very well know in Communication Engineering 1 we studied the commercial broadcast range for AM and FM and all. So for AM it is 535 kilohertz to 1605 kilohertz. Okay, 535 kilohertz to 1605 kilohertz. And for FM it is 88 megahertz to 108 megahertz. Okay, 108 megahertz. And all these technologies work in the ISM band. Okay, ISM specifically 2.4 gigahertz. Okay, all these things work in the ISM bands. So the second thing, okay, whatever I discussed here is the second thing, the frequency of operation. Okay, the frequency of operation. Okay, whether the antenna which I'm going to design should work on what frequency. Okay, so this is the second thing I need to consider, the frequency of operation. So as I said before, if I'm trying to design an antenna that suits for an AM communication system, it should work for this frequency, 535 kilohertz to 1605 kilohertz. If it is for FM, it is 88 to 108 megahertz. If it is for Bluetooth, Zigbee, Wi-Fi, it should be, it should work for 2.4 gigahertz. Or if I'm trying to design an antenna that should work for UWB, okay, ultra wideband technology or ultra wideband applications. So 3.1 to 3.1 gigahertz to 10.6 gigahertz. Okay, 10.6 gigahertz. For the entire frequency range, my antenna should resonate. In the sense, my antenna should be capable of transmitting as well as receiving for the frequency range from 3.1 gigahertz to 10.6 gigahertz. So before going to the design, I should be very clear with the application and the frequency of operation. So one more thing also we need to consider is the directional property of the antenna. Okay, the directional property of an antenna. That is the directivity. Okay, directivity of an antenna. Whether I need to design an antenna to transmit and receive omnidirectionally, or I need to design an antenna to transmit and receive directionally. Okay, if I want to my antenna should radiate in all the directions. Okay, in all the directions. If my antenna want to radiate, then I need to go for an omnidirectional antenna. Or if I want to radiate in a specific direction, okay, if I want to radiate in a specific direction, I need to go for a directional antenna. Okay, I don't want the radiation in these sides. Okay, I don't want the radiation in these sides. I want the radiation only in this side. Okay. In the total 360 degrees in these sides and all, you don't want the radiation, you want the radiation only in this direction. So in this case we need to go for a directional antenna. Okay, whether we are trying to design an omnidirectional antenna or directional antenna, that is the next thing we need to consider. So in this video lecture we try to design both the antennas, one directional antenna and one omnidirectional antenna and one directional antenna. Okay, so we very well know, in order to improve the directivity, so this is the parameter which defines the directional property of an antenna. Here the directivity of omnidirectional antenna is 1 and it increases. Okay, when the directional property of the antenna increases, the directivity value increases. So let us assume this antenna is having the directivity value of some 20 or something. So this is an assumption. Okay. So this antenna, so this is our starting point. This antenna is our omnidirectional antenna having the directivity value 1. This is the starting value of your directivity. And this antenna is directional antenna and this is having some directivity as 20. Okay. So we try to design one omnidirectional antenna and one directional antenna. Okay, so what is this directivity in the sense? So one of the popular way of increasing this directivity is building an array. Okay, instead of putting a single element. Okay, why we move into the concept of array in the sense? To improve the directivity. Okay, so instead of putting a single element, if we stack n number of elements and if we excite these elements properly, okay, if we excite these elements properly, then we can improve the directivity. Okay, you can achieve directional antenna by going into this structure. Okay, so the ultimate aim of going into the array structure is to improve the directivity or to increase the directivity. So if you are having a single element and if you are if you are exciting the single element, then you get omnidirectional pattern. Okay, omnidirectional pattern. And one way of improving the directivity is by increasing the length. Okay, you can increase the length, then you can improve the directivity, but you cannot extend the length beyond a limit. I hope you have studied all these things in your antennas and wave propagation. When you start increasing the length beyond lambda or 2 lambda, then the backlobe radiation starts increases. Okay, that is an unwanted thing. So in order to overcome that, we need to stop somewhere. Okay, we need to stop at lambda or 1.5 lambda, we need to stop. So other than that, what we can do is, instead of increasing this length, we can increase this length. Okay, so in this manner we can increase by stacking more number of elements horizontally, we can increase the length. So this won't affect the radiation. Okay, so if you, by doing this, we make the radiation directional. So as we discussed, first we try to fix the application. Okay, I'm trying to take an FM application, frequency modulation application. The broadcast range is 88 megahertz to 108 megahertz. This we very well know. And specifically, I try to design an antenna which should transmit and receive 93.5 megahertz. Okay, this is you very well know this frequency corresponds to Suryan FM, right? Suryan FM. Okay, so this is the frequency I have fixed, and the application is FM. So both I have fixed here, and I'm trying to design a half-wave dipole antenna. Half-wave dipole antenna. Dipole antenna. Okay. I'm trying to design a half-wave dipole antenna for this application which operates in this frequency 93.5 megahertz. So I'm very clear with my specifications. So we very well know the length of the half-wave dipole antenna is lambda by 2, where lambda is the operating wavelength. Operating wavelength. And we very well know the relation between lambda and C. Okay, lambda is equal to C by F, and your C is the velocity of light in free space, which is nothing but 3 into 10 power 8 meters per second, divided by our operating frequency is 93.5 megahertz. So 93.5 megahertz. If you solve this, you get the lambda value as 3.20 meters. Okay, 3.20 meters. Okay, and if you try to calculate lambda by 2, and your lambda by 2, here I write lambda by 2 is equal to 1.604 1.60427 meters. So now I have done some calculation, and I have obtained the length of the half-wave dipole antenna, which is equal to lambda by 2, where lambda is the operating wavelength. How to find lambda is putting this formula C by F. We can find lambda. In my case, the lambda is 3.20 meters, and lambda by 2 is 1.60427 meters. So how my structure would be, roughly how my antenna structure would be, in the sense I need to take, you also very well know antenna is simply a metal conductor. Okay, we are trying to excite a metal conductor with the signal in a particular manner. Okay, so I'm going to take a metal rod. Okay, metal rod of length, how much length? Lambda by 2, that is 1.60427. Okay, 1.60427 meters. Okay, this much length. Metal rod I'm going to take. Metal, one small, in the sense, a thin metal rod I'm going to take. So how I'm going to excite this metal rod with this signal, in the sense, at the center. As we very well know, half-wave dipole antenna should be center excited, and at the center I'm going to excite this antenna. Okay, so at the center I'm going to apply my signal, RF signal. Okay, so this is 93.5 megahertz with some amplitude. Okay, with some amplitude, I'm trying to excite this antenna with this signal. Then this antenna will radiate into the free space. Okay, electromagnetic waves come out of this antenna. Okay, in this frequency with 93.5 megahertz, the electromagnetic waves come out from this antenna. So, and also this antenna radiates omnidirectionally. Okay, this, since half-wave dipole antenna is an omnidirectional antenna, this antenna radiates in a
radiates omnidirectionally. So all these things, okay. Now what I'm very clear, I know the dimensions of the antenna. Okay, I'm going to design. I have designed a simple antenna, half-wave dipole antenna. For that antenna, I need only one dimension, the length of the antenna. Lambda. I also know the length of the antenna is lambda by 2, and for this frequency, what is lambda by 2? I have found out, and the structure. Okay, I imagined and I have drawn a structure for the half-wave dipole antenna, and this is how it should be. And further, what we are going to do in the sense, we are going to simulate this with the available CAD tool, EM CAD tool. We try to simulate this antenna. So there in the CAD tool, what you need to give as the input, okay, input to the CAD tool, input to the CAD tool, EM CAD tool, okay, input to the EM CAD tool. So what tool I am going to use is CAD FICO. So in this video lecture, I am going to use CAD FICO. This is the electromagnetic simulate CAD tool, okay, EM CAD tool. And what is the input you need to give as far as this tool is concerned, in the sense the dimensions. Okay, with the design dimensions, you need to create a CAD structure. Okay, you need to create a CAD structure. You need to take a metal conductor as a wire, and you need to center excite. Okay, you need to center excite the metal conductor with the signal. Okay, so this is what I am going to do with the CAD tool, and I am going to see how the radiations would come out of this antenna, whether I am getting the maximum radiation for the design frequency. So my design frequency is 93.5 megahertz. For this design frequency, I am getting the maximum radiation. Okay, I am going to see the 3D radiation pattern out of this antenna. Okay, how the antenna radiates, that I am going to see in the three-dimensional view. Okay, so all those things I am going to do with the CAD tool. Okay, that is our simulation part. Now we are in the design part. Okay, so now, as of now, we have designed half-wave dipole antenna, and we are ready with the dimensions. Since I told you we are going to design two different antennas, one omnidirectional antenna, one directional antenna. We designed omnidirectional antenna, half-wave dipole antenna. Next, we try to design a directional antenna. That is your Yagi-Uda antenna. Okay, Yagi-Uda antenna. Okay. This also you would have studied in your theory. So the design formulas and all we very well know. In Yagi-Uda antenna, the three different or the three important elements we have are one is the reflector, and the driven element, and the directors. Okay. So this is how your reflector would be large in size, and your driven element would be little bit smaller compared to your reflector, and your director is smaller than your reflector. This is your reflector, this is your driven element, and this is your director. Okay, so your director is smaller compared to your reflector and driven element. Okay, so and what are the dimensions corresponding to this structure? That is what we are trying to find out. Okay, so for reflector, the formula is 0.56 lambda. So from the literature or from your theory, you would have studied the reflector length would be equal to 0.56 lambda, and the driven element length is 0.5 lambda, and the director length is 0.45 lambda. 0.45 lambda. So as usual, I need to define my application as well as frequency. We already defined that. My application is FM and my frequency is 93.5 megahertz, Surian FM. Okay, and my lambda is 3.20 meters. Is it 3.20 or 3. Yes, it is 3.20 meters. So I know what is lambda, and by substituting here I can find out the value or the dimensions of my reflector. My reflector would be approximately equal to 1.604 meters. 1.604 meters, and my driven element would be equal to 1.52, approximately 1.56 meters. Okay, 1.52 or 1.6 meters, 1.529 meters, and my director length is 1.44. So my director length would be equal to 1.44 meters. So the spacing, okay, also I need to know the spacing between these elements, the spacing between reflector and driven element, and the spacing between driven element and the director. So this would be equal to 0.35 lambda, and this would be 0.125 lambda. Okay, 0.125 lambda. All these formulas, okay, all these formulas you would have studied in your theory, and in different literatures you would have find some difference in these formulas. That is fine, okay. So we can take we can take any one literature as a reference, and we go with that. Okay, in the literature I have seen, they have given all these formulas for the different elements. So I have taken that, and we are proceeding with that. So what is this space? 0.35 lambda is 1.12 meter, and this is 0.4 meters. Okay. So now I know all the dimensions of my Yagi-Uda antenna. I know reflector length, driven element length, director length, then spacing between all these three. Okay. So I can now, with the dimensions, I can go to the simulation. Okay. So in the CAD tool, I need to instead of taking single conductor, I need to take 3 conductors. Then I need to make one as the driven element, and the driven element should be excited. Okay, among these 3, the driven element should be excited with the signal. Okay, so whatever signal I'm going to apply should be applied to the driven element. Then this antenna will radiate directionally. Okay, in a single direction. Okay, this antenna will radiate in a single direction. Okay, so this is a directional antenna. Since this is a directional antenna, this antenna is going to radiate in a single direction, and the reflector and directors are parasitically coupled with the driven element. All these things you might be knowing. Okay, so that's all regarding your design part. Now we have designed 2 antennas, half-wave dipole antenna and Yagi-Uda antenna. One is omnidirectional antenna, other is directional antenna. One have the single element, and this is a 3-element Yagi. Okay, this is a 3-element Yagi. Now, since you have only 3 elements, so this is a 3-element Yagi. So, 3-element Yagi. If you put one more director, then it would be a 4-element Yagi. If you put another director, it is a 5-element Yagi. By increasing more number of directors, you can increase the directivity. As I already told you, by stacking more and more number of elements horizontally, you can improve the directivity. Okay, that's the thing. Okay, you can achieve high directivity by increasing the number of directors. Okay.